So Max Planck was kind of one of the first scientists to determine that classical physics had its limits when it came to light and energy, and that the theories that were around were not complete. And so he introduced the idea of quantization, and this is where the word quantum physics comes from. Quantum, and quantum just means, quant means how much, and so it kind of just means like a packet, a specific amount, that it's not infinite. There's a certain packet or certain amount of energy. Anyway, so what he thought of is, okay, atoms composing the hot metal vibrated. When they vibrated at increasing frequencies, getting faster and faster and faster, which would of course be smaller wavelength, this is what made the temperature increase. And so Planck then assumed that these vibrating atoms could only absorb or could only use quantized energy or specific amounts of energy. Okay, so again, so what he said was vibrational energies of the atom can only possess certain discrete values or certain quantities, not all quantities. And so he proposed that an atom could only have certain energies of vibration, so energy E, and he said, okay, they could only exist at certain frequency. So nu is frequency. He said they could only exist at certain quantized numbers. And here we're going to call n could be any integer, so like 1, 2, 3, 4, but it couldn't be like 1.5 or 2 3/4 or whatever. It could only be integers. And then it turned out that if you had these integers 1, 2, 3, 4, and you related energy to frequency with just these integers, then there was this other constant, which is now called Planck's constant, and it always came out that it had this value, 6.63 times 10 to the minus 34th joules times second. So those are the units of Planck's constant. H is such a tiny number, so it explained why this idea of quantization hadn't been thought about before. So we were getting into newer territory. So anyway, what this is again is showing you that energy is related to frequency, and it's related by this Planck's constant. But again, it can only exist at certain levels. So let's look at the next slide. I think it's on there. Again, so only energies could be like at 1h nu, 2h nu, 3h nu, 4h nu, nothing in between. So not 2.5h nu, or like I said, 1 3/4 or whatever. Could only be at whole numbers of this quantity, or at particular multiples of that quantity. These numbers 1, 2, 3, 4, 5 by n are called quantum numbers, and we'll get more into that as this chapter goes on. So again, these vibrational energies are said to be quantized or fixed, means that energy can only be released or absorbed in discrete amounts in certain sizes, not any old energy that they wanted, only very particular energies. So actually the picture I was looking for is even on the next slide. So yeah, so it was a revolutionary idea. It was a giant leap in thinking. But the idea is that energy can only be emitted or conversely absorbed in whole number multiples of h nu. So it's like, it's the idea, like staircases are quantized. You can only exist at this level, or this level, or this level. And if you go from this level to that level, you jump up. You have to go up this much. you know, and then a jump up again. So it's up this much. So this is quantized because you can't exist here at 1.5 steps or whatever. You can't. You can only exist at this level, this level, this level. This is in versus, this will be in place of what they thought was true, that energy could just be any frequency. That energy, or any wavelength, sorry, or any, sorry, let's back up. So this is just where energy can exist at any energy level and just continual increases, but it turns out that atoms can only exist at these certain levels and can only transfer from one level to another by these packets or by certain amounts. So, you know, here's the difference between those two. It can't exist in the middle. It can only give off or absorb this amount or this amount, etc. So hopefully that makes sense. And so that was sort of the first thing that got people thinking. And so Max Planck. There's another concern that didn't fit with classical theory, and this is called the photoelectric effect. So what is the photoelectric effect? This is an effect that electrons being emitted from a metal surface, so like if a metal surface was being heated or heated and giving off light, certain metals could only give off light of particular wavelength, or it would only happen if light of a particular wavelength was focused on it. It's kind of like the light had to have a frequency greater than some threshold frequency, otherwise it didn't work. I think the next slide has a good picture of it. And interestingly, the kinetic energy of the ejected electron didn't depend on how bright the light was, but only on the frequency. So I think the next slide has a better picture. Yeah, so here's the photoelectric effect. If we shine light on a piece of metal, it emits electrons. And here's just another picture. Here's purple light hit this metal, and electrons jump. And so, in fact, this will light up, or this is called a photoelectric tube. And actually, this is the very beginnings of the television was something like this, the photoelectric. So if you shine a particular wavelength on this, it will emit electrons and be, which will jump onto this positive electrode, and so you can get a current going. So according to classical wave theory, it shouldn't matter what the wavelength of the light is. So according to classical wave theory, the energy depends on the intensity, or in other words, the amplitude. How high is the amplitude? Not on the frequency, but of course they found out differently. So Albert Einstein was one of the first people to look into this, and he was able to resolve the paradox by using Planck's quantization findings. And so what he said is, okay, the light striking on the metal surface shouldn't be viewed as a wave, but instead as a stream of particles. And these particles were later called photons. So let's see if I can explain. Now, some of this is just the background and is not something you have to explain back to me, but just trying to set the background and give you some information about quantum. Anyway, so we see the energy of the photons proposed by Einstein then are proportional to the frequency. So energy is directly related to frequency, and that same Planck's constant, 6.63 times 10 to the minus 34 joule seconds, is still the proportionality constant. Now we don't have those whole numbers, but we'll see that this will come, those in numbers, this will come in just a minute. So Einstein said that frequency is directly related to energy, which we kind of saw earlier. You know, if you've got a low frequency, it seems like low energy. If you have a high frequency, it seems like higher energy. And so he used this to explain, Einstein used this to explain the photoelectric effect. Oh, that must be on the next slide. So the photoelectric effect, again, is the ejection of electrons from the surface of a metal when light shines on it. And it turns out that it depends on the, again, so it's just kind of repeating myself, it depends on the frequency of the light, not necessarily the amplitude or how bright it is, but how the frequency. And since we saw that frequency is related to energy, the higher the frequency, the higher the energy. So, for example, violet light, which has a higher frequency, shorter wavelength, higher frequency, will allow potassium to elect electrons. So if you shine violet light on potassium, it will kick out electrons. However, if you shine red light on it, which has a lower frequency, longer wavelength, lower frequency, it will never give off any electrons. So again, it's the frequency and not the amplitude that was important. So here's just an example of it. So here's my metal, my potassium metal, or some metal, and they're saying that there's a threshold energy. So here, green light at 550 nanometers, which is kind of moderate frequency, will eject an electron. Something with a smaller wavelength and a higher frequency will also emit an electron. However, red light, which is a longer wavelength and lower frequency, will never eject electrons. So there's a threshold frequency. And so this, again, was not explained by classical physics, but so the new model had to include this. All right, so this thought that this electron being ejected when struck by light as a photon implies that light behaves like a particle. So this, again, was really new thinking, because up until now, everybody thought of light as a wave, that it had that wave-like particles, wave-like properties. And now Einstein's saying, well, if we think of light as a particle, a photon, then that's what's happening here. The photoelectric effect says that light is acting like a particle. So again, what's happening when the photon hits the metal, the energy of the photon is taken up by the electron, and the electron is kicked out of the metal. The photon ceases to exist as a particle, and it is absorbed by the metal. So this brings us to what's called the wave-particle duality of light. So sometimes we can look at light as a wave, that it has wave properties, and sometimes we look at light as a particle, that it has properties of a particle. And so light is, so we have to look at both of these views of the same physical entity, that they're complementary views, and depending on how we look at it, it can act like a wave or it can act like a particle. So that's called the wave-particle duality of light. And you can kind of look at that. So you say, okay, E is energy of the particle, nu is frequency, and that's associated with the wave. So this equation sort of shows that duality of light. All right, so now let's get a little more practical. So now that we know that energy and frequency are directly related by this, and again, so we already had lambda, nu lambda equals c, and we knew c was a constant. So that's something you probably want to know these constants, because they'll be used a lot. So the frequency of light, 2.998 times 10 to the 8th meters per second. Now we have a new constant, which is Planck's constant, given the symbol h, and Planck's constant is 6.626 times 10 to the minus 34 joules times seconds. So if we multiply that by the frequency, so if our frequency is 1.255 times 10 to the 6th hertz, or inverse seconds, for example, so that's 1.255 megahertz, we can see that the energy is 8.316 times 10 to the minus 28 joules. So notice that the joules times seconds in that constant gets canceled, and so my answer is in joules, which is a unit of energy. So let's look at another quick example. When we see light from a neon sign, what are we observing? We're observing the radiation from excited neon atoms. If the radiation has a wavelength of 640 nanometers, what is the energy of the photon? So again, we want energy. We just saw that energy equals h nu. They didn't give us the frequency though. They gave us the wavelength. We also know that that frequency times lambda equals c. So we could do this a couple of ways. We could either first plug in lambda like we did before and find the frequency by using this equation, and then take whatever we get for the frequency and plug it into this equation. Or we could solve, and I think that's how I did it on this slide, but either way, you know, you could do it in 2 steps, no problem. But if you solve this and put c over lambda in for nu, then we have a new equation, c over lambda. So this is the same equation, just in a new way of writing it. So if I took c over lambda and I plugged it in for nu, so h times c divided by lambda gives me e. So I can plug this in, but again, be careful because c is in terms of meters per second. So we need to make sure that wavelength is in meters. So this has kind of got everything all at once. I think I would probably do that in small steps. So in fact, the first thing that I would do is I would convert 640 nanometers, well, 640 meters times 10 to the minus 9th meters. So if I want to, I could put 640 times 10 to the minus 9th, which is what this equals. And then h, 6.626 times 10 to the minus 3rd, joules times seconds, times c, speed of light, 2.998 times 10 to the 8th meters per second. Notice that the seconds will cancel, the meters will cancel, and actually the nanometers canceled when we determined that. So we're canceling out, we're converting nanometers to meters, canceling out the meters, canceling out the seconds, and my answer will be in joules. So again, you could do this in steps. You could first solve for frequency by solving this equation, converting lambda, find frequency, plug it in, or in this case, do it all at once.